the continuation of our session on gas to liquids. Our first talk after the break is by Dr. Chen, who will talk about probing Fischer Tropsch synthesis with acetylenic molecules. So,
good afternoon. My talk is probing Fischer Tropsch with acetylenic compounds. The objective of this research is to investigate the effect of co-feeding of acetylenic compounds, both the terminal and internal alkynes on FT, and to diagnose the possible pathways in FT on cobalt and iron catalysis. Using promolecules is effective way to study the mechanism of FT, and many promolecules have been used. It includes olefins, alcohols, and also some other C1 and C2 compounds. And this C1 compounds after this C1 compound sits on the surface of the catalyst, it decomposes and form this CH2, and this resembles the C1 monomer of FT from CO hydrogenation. It incorporates into the FT products, and it increases the Chen growth probability. And it is very interesting, this C2 compound. One is the this one, it contains carbon-carbon double bond. It can be easily incorporated into the FT and initiate the FT chain. But this compound, it does not incorporate at all. And this shows that chain initiation in FT is possibly by unsaturated two carbon dialysis. And when we use alkynes as promolecules, it is known that acetylene can initiate the chain, and absorption of acetylene is easier than that of acetylene, and absorption of CO is in between. Up to now, there is very limited very limited reports on co-feeding acetylenic compounds, and we have not seen reports on co-feeding acetylenic compounds on cobalt catalyzed the FT. And in this work, we will study the co-feeding of alkynes on cobalt and precipitated iron catalyst. The alkynes we used here is acetylene and long chain alkynes and phenol substituted alkynes. The catalysts we used are cobalt and iron, and long chain alkynes was added by a pump and as 10% pentane, and acetylene was added in as a gas mixture with argon, CO, and hydrogen. This is the hydrocarbon on co-feeding of acetylene, and we can say that this C1 does not change, and C2 up to C9 it increase, and the biggest increase is the dimer of this dimerization is not part of FT because it does not deactivate with injection of sulfur compounds. But this C4 dimer, it can effectively initiate the FT and form C5 and the up hydrocarbons. And this is the hydrocarbon products on iron catalyst. Compared to the cobalt catalyst, the biggest difference is the iron catalyst does not show much dimerization, and there is more hydrogenation to acid, and also the acetylene can be effectively incorporated into the products. This is the oxygenase after co-feeding acetylene, and we can see that the oxygen is formed on iron and the cobalt catalyst is very different. On cobalt catalyst, only one oxygen is formed. It is hydroformylation type of mechanism. It's the oxygenated form is just one carbon more than the added molecule, and this one is possibly the hydroformylation of the C4 primer. And on iron catalyst, we can see an oxygenase without in the normal FT, and with co-feeding of acetylene, the oxygenase in the whole range increases, and also the oxygenase is the distribution of the oxygenase is still follow the Anderson-Schulz Flour equation. This indicates that the oxygenase formation on iron catalyst is the FT type of Chen groups. And we also run FT at very low temperatures, and so the acetylenic molecules can initiate FT at 120 C, and in absence of acetylene, no FT were obtained on cobalt and iron catalyst, and also no FT was obtained with addition of olefins. And we use phytomarkers to distinguish the normal FT and those initiated by acetylene, and we use 4-phenyl-1-butane and 1-phenyl-propane. This is the GCMS of co-feeding 4-phenyl-1-butane. This is the molecule. It has carbon-carbon triple bond in the end, and we can see mainly two types of products. One is the straight chain hydrocarbons. It is from the normal FT, and the other type is phenyl hydrocarbons. This side chain is straight chain. And we also use the 1-phenyl-1-propane. This is be internal, and we get three kind of products. One is straight chain, one is the methyl branched. The C1 monomer was added here, and one is the straight chain products, and it is at first isomerization, and it's then initiate the chain. This shows the possible interconversion of two carbon additives. These two carbon additives can be formed by dehydrogenation of adsorbed acid, and it can also be formed by hydrogenation of adsorbed acetylenic molecule, and this shows both acid and acetylene can initiate the FT, and the conclusion here is alkynes initiate FT at more than 100 degrees below normal FT, and terminal alkynes initiate FT and form straight chain, and internal alkynes form both branched and straight chain, and differences exist in formation of oxygenates and with cobalt and iron, and it is possible that unsaturated two carbon additives are involved in initiation of the FT. And we thank DOE for the financial support. Thank you very much.
All right, questions? Okay, thank you again.